Okay, here we go. Video for log in the exponential worksheet here. Let's get started. So these are the explanation of the answers. Okay, so first thing, percent growth and decay. So we're just looking at the percent that we're looking for. So all exponentials can be rewritten in that form 1 plus r. So we're looking at what percent growth this is. So you're going to take the base, since this exponent is just x, and you're going to set it equal to 1 plus r. So if I subtract 1 across, you get 2. So r is 2. So to find the percent, though, this is the decimal equivalent. So you multiply by 100. So to take a decimal to a percent, so it's a 200% growth. So if you said something's tripling, it's a 200% growth. Okay. Likewise, this next one, though, but it's not ready for that. It's x over 2. So we're going to break up that exponent. So instead of being 3 to the x over 2, it's going to be 3 to the 1/2 power to the x. And the reason why that works is because 1/2 times x, of course, is x over 2. So same thing. And so I'm going to type 3 to the 1/2 power in my calculator, 1.73. Again, you must type that in the calculator. So you set that equal to 1 plus r. So again, we needed to get that exponent to be just x, just like here. So 1 plus r. So r is 0.73. It's positive, so it's growth. So 73% multiplied by 100, growth. Next one here, like if you actually said 4% decay, that's pretty darn good. But if I'm actually looking at this as annual rate, same thing. You'd go e to the 0.04, so we get this to the x power. All right, so type in this part here into the calculator, and it's 0.9607. So if you subtract 1 from that, again, it's always subtracting 1 because it's equal to 1 plus r. You get negative 0.039, so 392, so that's 3.92% decay because it's negative, it's losing value. We're losing 3.92% annually. One here, 0.83, another decay one. So again, this one's already to the x power, so we're good there. So it's 0.83 equals 1 plus r. Solve for r, so subtract 1, so it's negative 0.17. Multiply by 100, so that's 17% decay. All right, so the negative implies that it's decay. The next one here, compound interest. So we're looking at something that's, you invest it and it just stays. So you get the compound interest formula, which is this. N is the number of times in a year. So if it's yearly, N equals 1. Quarterly, N equals 4. Monthly, N equals 12. And daily, N equals 365. I'll do the continuously at the very end. So 365. So I'm just putting this equation into my calculator. So 5,000. And it's going to be 1 plus. Now 8%, do 8% divide by 100 to turn it into decimal, which is 0.08. So 0.08. N is 1. And the exponent is 1 times 10 because it's 10 years. And so that is 10,794. So 10,794 and 62 cents. There's a 4 there somewhere. 62 cents. Stylist didn't want to write. Okay, so do the exact same thing, but this time it's going to be a 4. And that makes this 4. And so it's going to be 40 for the exponent. And I would suggest if you have an older calculator to do the 4 times 10 together. Or otherwise, make sure you have parentheses around the 4 times 10. If you do that correctly, it goes up to $11,040.19. All right, if you do that correctly. Now I'm going to go ahead and change it from 4 to 12. And so this is 12 times 10, so we're 120 compoundings. See what that is. Type that into a calculator. And so that one is $11,098.20. So it jumps about $58. And then finally 365. So this is going to be turned into 365. 365 times 10. You put that in the calculator, and it's not going to be that much more. And it is $11,126.73. Okay, so those are all ones that utilize the compound interest formula. The second one, though, it's continuously. When you have continuously used, when you use continuously, you use the PERT formula. So the PERT formula, E is a number in your calculator, 2.71828. All right, that's talked about that in class. So E, and E is next to the number 4 in your calculator. So it's growth, so it's going to be positive 0.08. And 10. So you just type that in your calculator. Shockingly, it's only a couple of dollars, another dollar more to go continuously. It seems counterintuitive, but in reality, it ends up being just from here. It's not even a full dollar more. It's 97 cents more. All right, here's a graph to solve. Show a sketch of it and how long the truck will be. $60,000 will turn into $20,000. Some really good English in there. So I've got a $60,000 truck. Compound interest is depreciating 12% annually, so just like so. And we're going to use x. And the second equation is 20,000. So you do the graph, set the y equals. So y equal in your calculator and graph it and do second calculate intersect. My window, my y max, I need at least to be 20,000. Let's go up to like 70,000 for my y max because I want to see the y-intercept. You graph it, so it looks something like this. The point where they intersect is 8.59. So 8.59 years is when that truck's worth 20,000. Base formula. So that's how we can put this in our calculator. Some of the newer ones can actually do this without this. But change of base is a formula that we just do log of 5 divided by log of 2, or natural log of 5 divided by natural log of 2. Make sure you can get this correct answer. Make sure you put parentheses around that second 5 if your calculator's putting parentheses there. So 2.32 on that one. This one here, same thing, 0.63. Next one, log of 8 divided by log of 5, and that's 1.29. So again, make sure you can type that in your calculator correctly. And next one, personal finance calculator. I forgot to write 8% on there. So we're going to be compounding this. So you're going to go to your personal finance. I'm going to take a picture of the screen. For the first one here, 324. So first off, you're going to hit the app button to get to this screen. So you get apps, and that's going to do the finance one. So it's going to be apps, and then it says finance, and hit enter. So this 324, I did 12 months. And the reason, and I'm going to multiply by 27 because from 23 to 50 is 27 years. And so that gives you 324 here. 8%, I just told you that. Present value, that's what PV stands for, present value. There's initially nothing in the money or in there, so you don't have an initial deposit. Payments, $100. Future value, just ignore the negative here. It's a log thing, but you've got $114,000, and this P per year, that's compounds per year and payments per year. That's 12 because there's 12 months. We're doing this every month, and so you get $114,000 at the age of 50 just by doing just $100. Now to do this on the calculator, you're going to hit alpha enter to figure that out. We're going to get the highlighter here, and you're going to hit alpha enter to get that. For 55 years, we're going to do, again, 55 minus 23, all right? And so that's going to give you 32 years, so it's going to change that number up top here. Again, you hit alpha enter. For 55, it's 177,395 for 55, okay? And then again for 60, so now you're going to change the N, and you're going to do alpha enter here. So just from 55 to 60, it's going to turn into $271,000 and 640. If that's at 60, now I'll do it 62. So 55 gave me that one. Just 2 more years turns into 321,000. So it jumps 321,196. Jumps another 50,000 there just by doing, and you're only adding $100 a month. The money is doing all the work. 65, it's 412,000. And then finally it's 67, which is considered full retirement age for a lot of people, and that's 485,000. So just $100 a month, which is easily wasted, that you end up with if you do this at the very beginning when you get your first big boy, big girl job, you can end up with $500,000 essentially just by doing $100 a month, which is not a whole lot of investment, but most people don't do this. So just something to consider. Buying a house and $250,000, 8% interest. So you're going to put 15 years. So 15 times 12 is 180. So the thing that we're finding here is this payment amount. So present value, 250,000. Future value is going to be 0. You have to make that 0. We did alpha enter on this, and you find out your payment is $2,389 a month for a $250,000 house with an 8% interest. For 30 years, you change this to 360 and do the exact same thing. and you end up with $1,834 for your monthly payment for a $250,000 house. So substantial payment, and that's without the taxes and insurance. That's just simply what you're paying the bank. All right, moving on. Okay, find the inverse. So switch the x and the y, and switch the x and y. So it's 3 to the y, and with an exponential, we're just going to simply rewrite this as a log now. So this is the base 3. And the exponent goes on the other side. This is the definition of a log. So this is the inverse for y equals 3 to the x. Saw that several on the homework. All right, number 11. Log equation using regression. So you go stat on your calculator and edit. And this is going to be list 1 and list 1 and list 2. And we're going to, since we want the log equation, we're going to do a log regression. Put this in, this is what it's going to look like, and then we're going to hit stat again. So this is the stat button we're doing, and we're going to do calculate. So stat and then calculate, and it's going to be log regression. So you'll see it's ln, so ln regression, so that stands for natural log, so we're going to use that right there. So I've done that, and so I've got the a value and the b value, so my equation a goes in front here, so I've got 0.04 plus 1.06 natural log of x. And so that's the equation. I made this up. This is a very great data. How do I know it's so great? This correlation coefficient, or 0.999, tells you how good it is. Closer to 1, it's the better. The reason why it looks so wonderful is that as x increased, so too did y, but x had to jump big. Like it went from like 20 to 50 and 50 to 100 and 100 to 250 in order to get those y's to increase. And that's a slow growing function, just like a natural log. On calculator here, so solve and simplify, or simplify and solve. So these are without a calculator, so this is your understanding of the definition here. So 2 to what power is equal to 8? And so that's 3, because 2 times 2 times 2 is 8. So if you go 2, 4, 8, 16, like knowing those is really important. It's 3. The next one, likewise, same thing. So 16 was 4. So 2 to the 4th power is 16, but it's 1/16, so that's a fraction, so 2 to the negative 4. Log of 1, no matter what the base, is going to be 0, because log of 3 to the 0 power is 1, so this is 0, so cause that's 0. And then this one here, so we can use the definition 2 is the base, exponent is 3, equals x, so x is 8. If you are in a non-calculator such as this, natural log of x equals 4. You're going to use the definition here. So the base of natural log is e. So this is basically just testing your knowledge. Do you know that the base is e? So it's e to the 4th. E again is that special number 2.7828. Now the next one here is a good problem. It's a subtraction problem. So subtraction really is division using our log properties. So this is log of 48 over 3. The bases do nothing. They don't change. I mean, they don't change at all in this. And now 48 over 3 is 16. So now I've got log 16 base 2. So 2 to the what power is 16? That's 4. Okay, so we use the change of base, or condensing, to get to that. Let's do the same thing here. This addition problem, it turns into log of 10, because addition really is multiplication, so 5 times 2 is 10. Now the base on this log, it's a common log. It's not written, but it's 10. So 10 to what power is 10? The answer is 1. All right, number 8 here. Graph include a table for these two problems, 8 and 9 here. So exponential, we're going to choose our x values. So we're definitely going to use 0. There's no horizontal shift here. And we're going to go increments of 4, because that makes a nice exponent. All right, so at 0, the y-intercept is 5. And we're tripling every 4 units of time. So from 5 is going to turn into 15, 15 to 45. Yes, I would expect you to know that 15 times 3 is 45. You can do it. And if I'm tripling this way, then going back this way, I'm 1/3. So it's okay to write 5/3, right? Which is like 1.67. So if I'm making my graph here, make your increments in 4, since that's what our table's going by. So there's less work here. And my y values, 5 seems like a good number. 5, 10, 15, 20, etc. I'm going to run out of page, etc. So we'll just do the first two. So 0, 5, right there. 4, 15, 845 is like up here. It's up top. It's up top. It's beyond the screen here. -4 5/3, that's like down here. And so you got yourself an exponential. Make sure you do not let this exponential graph cross this x-axis. That is the horizontal asymptote. Big points taken off if you do that. If you let it cross, bad, 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 bad. Its domain is all real numbers, so domain is -infinity to infinity, and the range, though, is from 0 to infinity. Likewise, this next one here, we're going to go ahead and make our table. Our table this time is going to go by 5s, so 0, 5, 10. I'll go -5. You could do more, don't need to. The y-intercept is 20, so 20 is at 0. There you go. And we're 1/2 each way, so 10, 5. So if I'm 1/2 this way, that makes me double the other direction. So if I'm making a graph here, I should go by 5s and the x. Make sure you label that. And then the y's, 10s would be a nice number here. You get to choose that, so 20, etc., 30, 40. So -5, 40, let's make that green. -5, 40, 0, 20, 5, 10, and 5. So it's going to fall. So this is decay. And again, I know that this is looks like this because this is an exponential. You have to recognize that it's an exponential, this is an exponential, this is log, right? So know the different graphs. Right? So these next ones, 10 and 11, we're just quick sketching. We're looking for the locator point, the domain and range, and we're looking for the asymptote. So it's been shifted up 2, because that's that +2, so dot, dot, dot. The locator point here is at 4, because that's what makes this 0, so 4, and it is 5 plus 2 every single time. The reason why, again, is because 3 to the 0 power, because when I put in 4, I get 0, so 3 to the 0 power is 1, so it's 5 times 3 to the 0 power plus 2, so this is 1, so 5 plus 2, and so 7, so 4, 7, made a mistake and erased it, so 2, and so 4, 7, 1, 2, 3, 4, 5, 6, 7, and make sure that clearly indicates that it's a growth one. And so just boom, there's my sketch. My domain is all real numbers. My range here is from the horizontal asymptote on up, so it's 2 to infinity. Likewise, the next one here, this one's decay. -4, 8 is my locator point, so -4, 8, and 8, so by there's 8. And the horizontal asymptote is at -2, so we've got a horizontal asymptote way down here. This time it's decay, so it's going to come down to that. And my domain is still all real numbers. My range, though, would be from -2 to infinity. So lowest number always comes first when we're given this in interval notation. All right, some log graphs. So these were exponentials. Now we're going to do logs. And so logs, a little bit different. We're looking for the vertical asymptote. So remember, we set the inside equal to 0. That tells us the vertical asymptote, or also known as the horizontal shift here. So 7. 1, 2, 3, 4, 5, 6, 7. So there's my vertical asymptote. And then you set that equal to 0 for the horizontal asymptote, or a vertical asymptote. You set it equal to 1, the inside equal to 1, to find out where the locator point is at. So if you solve that, you get x equals 8. Now if I plug in 8 into this, I'm going to get log of 1, which is 0. And that's the whole idea. So my other part of the locator point is the 9. So 8, 9. So about yay. And then there's no reflection here. So we're going to start at the bottom and we're going to go up. Next one. This one does have a reflection. Still same exact thing. So you set the inside equal to 0. Oops, hold on. Let's go back to this first one here. My domain now is not all real numbers. It goes from my vertical asymptote here, which is at x equals 7. So it's going to be from 7 to infinity. Again, it's parentheses because it's not including 7. And then my range this time is all real because remember it's the inverse of an exponential. All right, so vertical asymptote, -5. Okay, -5 is your vertical asymptote. Again, I set it equal to 0. If I set it equal to 1 and solve that, you're going to get x equals -4. So the vertical asymptote, or the locator point's at negative 4, 6. So 6, 1, 2, 3, 4, 5, 6. Now, there is a reflection. It's over the x-axis. It would have happened at the very beginning. So instead of being like this, the reflection is like this. So again, so it's going to be falling. So it's going to fall. So my domain here is negative 5 to infinity. My range is all real numbers. First steps, bring up the coefficients. Boom. Bring up the coefficient, bring up the coefficient. So I've got log of x to the fourth plus log y cubed minus log z squared. Now, addition turns into multiplication. So this is log of x to the fourth y cubed. And subtraction turns into division. So z squared on the bottom. There's only one log when you write this out. All right. Next one here. Bring up the coefficients. Natural logs, same as logs. So, and then I'm going to work my way to left to right. But so natural log y squared minus natural log z cubed. So this is going to, so addition in terms of the multiplication. And again, the reason why this is true is because these are truly exponents. Subtraction turns into division. And we have ourselves, now I don't need the parentheses, but it's just pretty. Expand it out. So instead of condensing, we're going to expand. There's going to be 3 logs because I've got the 10 that's going to get its own log, the x cubed that's going to get its own log, and the y is going to get its log. All right, so this is going to become log 10 plus log x cubed minus log y. The division is going to be last. My base on these is 10 because it's a common log. So this coefficient comes down, or the exponent comes down as a coefficient, so it's 3 log x. And this one here can actually be simplified because 10 to the what power is 10, and that's 1. And so that is one that could be simplified. All right, so that's expanded. Next one, you don't bring the exponent down until it's around everything. So in this case, the 3 applies everything. So the 3 is going to come down. I'm going to write that out there in front with a bracket. And I've got natural log of 4 plus natural log of x. And again, minus natural log of y. Again, oops, bracket. Brackets are just like parentheses if you use parentheses that have been fine too. But again, breaking up the multiplication with addition, and division is subtraction. All right. So now, again, non-calculator, solve and get answers without logs. So this is going to use the 1-to-1 principle. So 16 is 2 to the 4th. So using the 1-to-1 principle, if we can rewrite these with the same base, now once you have that, the exponents must be equal to each other. So that is true if x equals 9. So set the exponents equal to each other, but you have to have the same base. It's got to be the exact same. It can't be the different bases. So, all right, so that one's done. But you have to get them isolated before you do that. So like, let's look at this next one here. It's not isolated, not ready for it. So we're going to get rid of the minus 1. So it's going to add 1. And so 324 divided by 4 is 81. So I've got 4 here. Oops, I guess I should probably do that all the way out. So this is 324. Yeah, a little math here. Divide by 4. I'll try to make a little smaller number, I guess, maybe to be nice on you. So this is 81. So now we're going to go ahead and rewrite this, change 81 into 3 to the 4th. So then 2x, so now that this is base 3 and this is base 3, 2 to the x must equal 4, so x equals 2. So the 1-to-1 principle, again, everything's got to be the same, so therefore that you can set them equal to each other. This next one, log problem, it's simple. The insides must be the same because there's nothing else. It's just simply log and equals log. So the only way it's possible is if the insides are equal. So you can set the insides equal to each other. That's the 1-to-1 principle. And you solve the simple equation. So now you just subtract the x, add the 4, and so you get 2x equals 5, divided by 2. So x is 5 halves. Again, that's 1-to-1. Now there's These next ones are, I'm rushing a little bit. I don't know if I'm going to be able to get to all of this. Solve, you're going to isolate a log. And so we're going to isolate this log here. So I'm going to add the 4 across. So add the 4 across, it makes 10. And then I'm going to divide by the 2. So I've got 5. So I've got log of 3x plus 1 equals now 5. Because when I did add 4 and then divide by 2, I get 5 there. So now I'm going to rewrite this. Once I get this down, I'm going to go ahead and use the definition. So 10 to the 5th power, because this is common log, equals 3x plus 1. So 10 to the 5th power is a 1 and 5 zeros. And it's okay that I'm going to leave this as a fraction when I get this done. So I'm going to get x by itself. So subtract 1 and subtract 1. So you get, 9,999 equals 3x. So x is whatever 9,000. If you divide by 3, you get 3,333. I'll make them smaller numbers for your test. Okay, the 30-minute mark, so I got to rush here. This next problem, condensing. So if you have 2 logs, you're going to use your log properties to condense this. So this becomes log. And so this is a good old-fashioned quadratic problem because x times x plus 4 is x squared plus 4x. I distributed that. Equals 5. Now I'm going to use my definition. So 2 to the 5th power is 32. So now I've got 32 equals x squared plus 4x. Oh, man. And then I'm going to subtract the 32 across. So I get 0 equals x squared plus 4x minus 32. Now, given that this is a non-calculator, this better be factorable. Otherwise, you got a quadratic formula on your hands. And it does factor. All right, so it does factor to be x plus 8, x minus 4. And so you get 2 answers here, -8 and +4. Now, these are both correct. However, one is extraneous. If you go back to the original problem, if I plug in -8 in there, it doesn't work because you can't have the log of a negative number. So it's just 4. That one's a tough one. That last one. Now solve the exponential. So add 7. So you get 4 times 3 to the x. So you isolate in the exponential just like you're isolated the log. So divide by 4. So 3 to the x equals 5. Now, you could rewrite this as a log, but there's a helpful to look at it like from the point of an advanced problem. You can take the natural log both sides, allows that log property, the exponent, to come down. And again, you could have rewritten it as a log and be totally correct. So you get x equals natural log of 5 over natural log of 3. If you had rewritten it as a log, it would have been log of 5 base 3. And so this one's okay because it's a non-calculator. Oops, non-calc, so you just leave it as this right here or this. Either way is fine. Again, isolation is the key for logs and exponentials. Next graph, we have it's moved right 3 and up 5. So the vertex should be at 0, 0, but instead it's right 3 and up 5. I think that's 3. Oops, make that dot a little bigger. And then it's going to, if I were to make actually a table, so that's where your vertex is at, but it's up 3 and over 5. If you made a table and plugged in each side, one number left and one number right, you're going to find out it's 7. And there you go. That's a nice quadratic. And factor, 2 numbers multiplied to be -18, combined to be 6, so it's x plus 6, x minus 3, because I need +3, not -3. This next one, 2x squared minus 1x minus 6, -12 here. So we're looking for 2 combinations, -4 and +3. I'm doing this quick because I only have 1 minute left of timing. By grouping, pull out a 2x, so I get x minus 2, and I pull out a 3 in the next one, 3, so it gives me x minus 2. So I get 2x plus 3, x minus 2. Okay, last problem, solve this one. This one is a one that it'd be the quadratic formula. It'd probably be in a calculator one so that you could use the quadratic formula, but I'm going to use the quadratic formula on this. So I've got -b, so it's going to be 3 plus or minus b squared. So it's 9 minus 4 times a, which is 2, c, which is -8. Again, with a quadratic, you'd have to be able to needs to be equal to 0. It's got to be equal to 0. And you get 3 plus or minus the square root of 73 over 4. Whew! Long video. All right. And hopefully this is helpful for you.